Okay, so this is the first of the videos for chapter 3. In this chapter, we're going to be covering several topics related to properties. So first, we're going to look at the concept of a pure substance, followed by discussing the physics of phase change processes. And we're going to be looking at something called property diagrams. We're going to look at using tables in order to quantify properties. We're going to be looking at an ideal gas, and we're going to be looking at how to apply the ideal gas equation to some problems, followed by compressibility factor, and then kind of ending with some other what we call equations of state. All these topics are related to being able to quantify properties of a system that are used in a first law analysis in order to quantify energy transfer terms. So let's start with what a pure substance is, right? A pure substance is a substance that has a fixed chemical composition throughout, right? It can be a single compound, it's a single chemical compound or element. A mixture of various chemical compounds may also qualify as a pure substance. Here's an example. If I have a tank of nitrogen, it's a pure substance because it's all nitrogen. But also, if I have a tank of air, air is also considered a pure substance, even though it's composed of several different forms of gases, but it's all kind of mixed as a homogeneous mixture, right? So that would be regarded as a pure substance. An example of something that is not a pure substance is, for example, oil-water mixtures, right? If I mix oil and water, they eventually separate, so that would not be considered a pure substance. Phase. A phase is a distinct molecular arrangement that is homogeneous throughout and separated from others by easily identifiable boundary surfaces, right? So there's basically what you've probably learned at this point is that there are three basic phases. One is solid, right? In a solid phase, molecules are arranged in a three-dimensional pattern that is repeated throughout the space. So molecules continuously oscillate about the equilibrium positions, and the velocity in the molecules depends on the temperature. Next would be liquid. Liquid molecules are not fixed in any position relative to each other, and they can rotate and translate freely. So molecular spacing is similar to that in solids, but in general, the distances between the molecules are larger in a liquid than in a solid. And then finally, gases. Gases where the molecules are far apart from each other and the molecular order is non-existent. Molecules can move about at random and continually collide with each other and the walls of the container they are in. So let's look at what we would call phase changes, right? And in thermodynamics, phase change is very important, especially in regards to water, because water is often the working fluid of for example, a power plant. A power plant uses water and circulates water through a cycle where in that cycle it's changing phase between liquid and gas and using that phase change in order to convert energy. So it's important for us to understand what's going on when water turns from a liquid to a gas and a gas back to a liquid. And basically there's going to be 5 different, I wouldn't call them phases, but 5 different regions of phase change when going from liquid to gas or liquid to water vapor, right? Because that's what gas water is. It's water vapor. So let's look at an example. Let's consider a piston cylinder device. In that piston cylinder device, we have water at 20 degrees Celsius at a pressure of 1 atmosphere. We're going to examine what happens to the substance as it's heated. Another example would be just let's picture that you guys poured water at 20 degrees Celsius into a saucepan. We're taking that saucepan and we're putting it on the burner in your household and turning on the gas. and heating up the water, right? The first stage is going to be a region called a compressed liquid, right, or a subcooled liquid. What this means is that the water is not about to vaporize, right? So as I add heat to my water, what happens? The temperature of the water increases, goes from 20 degrees to 30 degrees to 40 degrees to 50 degrees. So basically, heat transfer to the system causes the temperature to increase and the fluid expands. And also what happens if I remove heat, right? If I remove heat, well, the temperature will decrease. So heat transfer loss causes the temperature to decrease. So that's region 1, called compressed liquid. Region 2, called saturated liquid. It's really important. Saturated liquid is when you're basically just about to boil, right? So I hit 100 degrees Celsius because at 1 atmosphere, water boils at 100 degrees. So what happens? Well, a phase change is about to occur. So what happens is I continue to add heat to water that is at 100 degrees. Well, if I add more heat at 100 degrees, the water temperature does not change. It still stays at 100 degrees because what's going to happen now is that the water is going to turn from liquid to gas, right, to water vapor. So as it turns from water, what happens is I add more heat, it causes a phase change. If I remove heat, it causes the liquid to cool, right? If I lose heat, the temperature goes down. So that's what a saturated liquid is. A saturated liquid is a water or any liquid. It's a liquid about to boil. It is at the boiling point and boiling. So that's the second stage. Third stage is called a saturated liquid vapor mixture. What does that mean? That means that liquid and vapor coexist, right? So what does that mean? That means now as I continue to add heat to my boiling water, what happens is I continue to add heat. And this gets confusing because people are like, why doesn't the temperature go up? The temperature is not going up because what's happening is now added heat is causing the liquid water to turn into gas water or water vapor. It's causing a latent heat exchange. That's what latent heat means. The word latent heat means phase change energy. So it is causing the liquid to go from saturated liquid to what's called a saturated vapor, right? It's going from gas or water that is about to evaporate to vapor that just evaporated. So as I continue to add heat, phase change is occurring. It is a present tense and occurring. So both liquid and vapor coexist. So any added heat causes more liquid to vaporize. Any lost heat causes the vapor to condense. That's called a saturated liquid vapor mixture. That's the third region. The fourth region is I've continued to add heat to the system, and now all of my liquid is gone and all turned to vapor, just to the point that it all turned to vapor. I'm still at 100 degrees, and all my vapor is gone. So a saturated vapor is a vapor that's about to condense. So what happens if I lose heat? If I lose heat from this, it goes from vapor back to liquid. If I add heat, if I continue to add heat to the system, the temperature increases because now there's no more liquid to evaporate. So now that all of it's evaporated and the temperature of the gas is at 100 degrees, now the temperature of the gas or of the water vapor will increase, right? So that's saturated vapor. Which brings us to the next stage after saturated vapor, and it's superheated vapor. Superheated vapor means a vapor that is not about to condense. So any added heat to the water vapor makes the temperature go up. Any heat loss makes the temperature go down. So again, these are the 5 regions. Compressed liquid means as I add heat to my liquid, the temperature increases. As I take away heat from my liquid, the temperature goes down. Saturated liquid. I have heated my liquid up to the point that it's boiling. So now as I add heat to it, it causes a phase change from liquid to gas. If I take heat away from it, it causes the temperature of the liquid to decrease. Third stage, saturated liquid vapor mixture. At this point, I have liquid and gas coexisting, where if I add more heat, I get more gas turned from liquid. If I take away heat, I get more liquid converted from gas. Saturated vapor. This is at the point that now all of my liquid has turned to gas. Just suddenly, it's all turned to gas. It's at the point that it's all gas. Still at the same temperature, still at the boiling temperature. In this example, still at 100 degrees Celsius. If I take away heat, it causes some of the vapor to condense back to liquid, and I'm back into the saturated vapor liquid region. And if I add heat to it, the temperature of the gas increases, putting it into the superheated vapor region, which is the last area, or the last region where superheated vapor is where if I add more heat, my temperature of the gas goes up. If I take away heat, the temperature of the gas goes down. So those are the 5 regions of phase change between liquid and gas. It's very important to understand these. So what I'm going to do now is just kind of jump ahead a little bit, and I'll go ahead and paint a graph here, right? So this is where we're going. If I were to go ahead and draw a property diagram, I'm going to call this temperature on the y-axis, this specific volume on the x-axis. Remember, specific volume is the inverse of density, right? So let's call this 100 degrees Celsius, right? That is the boiling point of water at 1 atmosphere. So what happens? Let's say I start my water here, right? This is 20 degrees Celsius. What's happening is that I heat water, right? I'm heating it, I'm heating it, I'm heating it. It's increasing in specific volume, right? It's expanding as I heat it, increasing in specific volume, and increasing in temperature, increasing until I hit this point, right? So this is state 1 at a compressed liquid. This is state 2 at a saturated liquid. What happens now? Well, as I heat it, the temperature remains constant, right? Why does it remain constant? Some people still have a hard time when I teach this class for the first time. Why does the temperature remain constant? I'm heating up, the temperature should increase. Well, the temperature only increases when you are out of the phase change region. This is phase change. Any heat adding is causing this to change from a liquid to a gas until I get to state 4. That is a saturated vapor. So anytime in this region, this is going to be stage 3, right? Any in this region is stage 1, compressed liquid, meaning that as I add heat to the water temperature increases. Then I hit that 1 point state, state 2, saturated liquid. Then as I add heat to it, what's happening is that it is in the process of making the water change from liquid to vapor. And that whole process occurs until all of my vapor disappears, until all of my liquid disappears and makes it into a saturated vapor, which is this point. So that means that this whole area is a saturated liquid vapor region where both gas and liquid coexist at the same time. What happens when I hit this point? Well, as I add heat, my vapor is just going to increase in temperature. All this area is going to be in region 5, which is a superheated vapor, right? Keep adding heat and the temperature of my gas is going to increase. All this happens at a constant temperature, constant pressure, 1 atmosphere, right? Heating, boiling, and then heating again. What if I'm at 180 degrees? What does that look like? Well, water boils at 180 degrees when the pressure is 10 atmospheres, right? You got to understand that we all kind of understand water boiling at 100 degrees because it's all relative to the pressure that we exist in. We exist in 1 atmosphere. So our practical day-to-day lives, we have always understood the water to boil at 100 degrees Celsius or 212 degrees Fahrenheit because that's what we're used to in the lives that we live. But realistically, the boiling temperature of water changes with pressure. The higher the pressure, the higher the boiling point. You know, a case example would be someone who lives in Denver, right? If you live in Denver, Colorado, I think it's called the Mile High City because the city lies at an elevation 1 mile higher than sea level. Water boils a little bit at a little bit less than 100 degrees, something at like 98 or 97 degrees. Well, it's because the pressure is less, right? It takes longer to boil an egg in Denver than it does at sea level because, well, the water boils at a lower temperature. So if I were to go ahead and redraw this graph, right, this line, for 10 atmospheres versus 1 atmosphere, I'd find something like this, where my water temperature would start here, increase, 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 until I start boiling at 180 degrees Celsius is when I would start boiling. That's my saturated vapor, my saturated liquid. Again, phase change would occur until everything is turned to gas. And then as I add more heat, my temperature of the gas goes up, right? That would be, for example, at 10 atmospheres. As I continue to do that for different temperatures, what we're going to find is there's something called a saturated liquid line, right? This line that I just drew connects all the points at which different saturated liquid states occur for different pressures. And then the same thing, as it curves down, I'm going to realize that this is a saturated vapor line, which connects all the different saturated vapor states at different areas. So this side of the curve is what we call the superheated vapor region. This side of the curve is called the compressed liquid region. This area is called the saturated liquid vapor mixture region. Because anytime you're inside of this curve, you have both gas and liquid coexisting at the same time. Anything on this line is called saturated liquid, so it's just called the saturated liquid line. And then this is called the saturated vapor line. Okay? This is what is called a classic diagram that we're going to be using later on, the draw out processes, in order to be able to see the phase of the water during a thermodynamic cycle. We're going to take time to re-explain this about maybe 2, 3, or 4 different times throughout this whole chapter, so that this graph, the idea of phase change for a liquid, it's not just water, we're going to be dealing with other substances as well, but the phase change is really important because the amount of energy and the type of process that occurs is going to be different depending on what side of this curve you're on.